Hello friends, today we are going to discuss inventory models. What is inventory? Inventory is the term of goods available for the sale and raw materials used to be produced, goods available for sale. Inventory mainly represents one of the most important assets of a business because the turnover of the inventory represents one of the primary source of revenue generation and subsequent earnings for the company shareholders. Inventory is the stock of any item or list of stocks of any items or resources used in an organization. The objective of inventory management has to keep enough inventories to meet the customer demand and also to be cost effective. Various costs associated with the inventories are purchasing cost. As the name suggests, the value of an item is in unit purchasing cost or production cost. Many times what happens when order size increases. For example, we are going to order uh, 10 kilo to 200 kilo. Then for the cost of 200 kilo, it will be less. That concept is well known as discounting. At that time, purchasing cost varies. Okay? Per unit purchasing cost varies. Capital cost. The capital cost, as the name suggests, it is other amount invested in an item. Capital cost is an amount capital not available for the other purchases. Capital cost is mainly used in many times in share market where you use your capital, that amount to invest in some shares, and then you expect to get some returns. Okay, as the same logic, here we are investing in the inventories, we are selling them, we are earning profit from them, and that earning profit is the interest for that capital amount. Another cost is ordering. These has have many names: ordering, procurement, replenishment, acquisition cost. But as first name suggests, ordering cost, it is just an ordering cost, starting from quotation to up to receiving the inventories from the supplier. Okay, there are two types of cost. First cost is a fixed cost, and another one is a variable cost. Fixed costs do not depend on the number of orders or quantity of the orders. Okay, both are different things. Number of orders is represent frequency and quantity is represent quantity. Whereas the variable cost change with respect to the number of orders placed and as per the demands. There are generally they are generally classified under the following heads: purchasing, inspection, and accounting. Now, what is purchasing? Now, purchasing cost involves many things. Means clerical and administrative cost associated with the purchasing, cost of the placing the order, follow up, receiving, evaluating quotations, everything comes under the purchasing section. Another part is the inspection. As the name suggests, the cost of checking material after they are received by the supplier for quantity and quality and maintaining records of that receipt. Accounting, as the name again suggests, the cost of checking supply against each other, making payments, making records of the purchases are all comes under these heads. And these are the variable cost. Okay, transportation cost. There are, as name suggests, these are the expenses involved in moving products, moving from supplier to retailer, retailer to customer, Zomato, Pizza, Burger. All these transportation costs are involved in this inventory section. Cost, transportation cost. Another important is a holding cost, popularly known as inventory carrying cost. It has many sections: storage cost, handling cost, depreciation, taxes and insurance, cost on record keeping, product deterioration, spoilage, breakage. Everything comes under the holding cost. Um, as the name suggests, the storage cost, suppose I am the supplier, I have the inventories uh, in my godown. Suppose that godown is rented, that rent is comes under the storage cost rent. If that is ice cream, then that cooling charges, electricity required, or whatever, heating charges, lighting charges, everything comes under that holding cost. Okay. Another section is shortage cost. Shortage cost, many times shortage cost is or penalty cost. Suppose if I have contract with some organization and I failed to supply the inventory when the company requires it. At that time, as there is a contract, I have to pay some penalty. That is the shortage cost. If there are some unsatisfied demand, they can be satisfied at later stage, but there must be some penalty that or such type of orders are called as a back order cost. Loss of future sale, loss of customer goodwill. Though customer goodwill cannot be measured in the monetary terms, but it is a loss, and I think, or many companies think that it is a great loss. While goodwill, losing a customer goodwill is not a good for any company. Loss of profit contribution, probable profit contribution will be lose. These are the inventory models. Classification of inventory model is based on based on the uh, demand, and if the demand is deterministic, fixed, then deterministic inventory model. If the demand is random, then it is classified as a probabilistic inventory model. We are going to see one or two deterministic model and one or two probabilistic deterministic model. Both are again classified with respect to fixed quantity, fixed period. Let's see some terminology that involve in inventory control. Demand, as the name again suggests, it is the number of the items required per unit time. The demand may be either deterministic or probabilistic in nature. Okay. Okay. Let's take an example of an ice cream. Okay. Suppose there is an ice cream parlor, and there is a demand. Suppose there is a deterministic demand. There is a fixed demand of 1200 kilos per year. Okay. 1200 kilos per year, then for per month the demand is 100 units, 100 kilograms. Okay, that is the demand per unit time, per unit of time, per year, per month, per day, whatever. Then ordering cycle, suppose that shopkeeper is calling the supplier and asking for the ice cream, 100 kilogram of ice cream. Then for the year, such order, there are 12 orders per month. Okay, then here ordering cycle is a month, time between two successive orders. Lead time, he orders the supply for the ice cream, he receives the order, the difference between both is called as the lead time. Okay. Safety stock, suppose he orders 100 kg, but supplier told him that he will deliver in 2 days. Okay, for that 2 days there must be some demand of ice cream, so he will keep some ice cream in a buffer stock, in a safety stock. If the supplier fails to supply in 2 days or 3 days, there must be some stock. So it is called as the buffer stock or minimum stock. It is the stock or inventory needed to account for delays in the material supply or to account for sudden increase in the demand due to rush orders. Inventory turnover. If the company maintains inventories equal to 3 months consumption, it means that inventory turnover is 4 times a year. In our case, it is 12 times a year. Okay. Reorder level. Suppose if that shopkeeper sells uh, 4 kilo 4 kilo of ice cream a day. Okay, then and a shop supplier supplies him ice cream in 2 days, then whenever there is a order level, What is the order level? For 2 days, the required expected quantity is 4 multiplied by 2, 8 kilogram. So whenever there is an inventory where there is a stock of 8 kilogram of ice cream, then he must reorder. He must send order to the supplier. That is the level is called as the reorder level and reorder quantity. Normally these quantities equal to the economic order quantity. We have to find out this economic order quantity, EOQ. Single term, single item, continuous demand, and instantaneous replenishment. Here we are considering the deterministic model. You can observe here the inventory level, and as per the demand is, as the demand is constant, uh, you can observe it here. There is no randomness in inventory level, decreasing inventory level. At this time point, the order is given. Within fraction of a second, he receives the order, and the inventory level reaches to Y. Whenever inventory level reaches to 0, he orders and he gets in a fraction of second. Now what happens for that? This period T naught is called as the cycle, ordering cycle. Okay, at this time point he has Y inventory level Y, he has inventory level 0. Average of both is Y plus 0 divided by 2, so Y by 2. So he has to hold, on an average he has to hold Y by 2 such inventory. Okay, so total inventory cost per unit, we have to calculate it, we have to minimize it. Purchasing cost, it might be fixed for all. Setup cost, that is ordering cost. Suppose we have to file a quotation or something. Okay, holding cost for the ice cream, for the ice cream case, we have to hold that ice cream for 1 month period, so that is the holding cost. Shortage cost, if there is any penalty, then it is the shortage cost. The graph indicates nicely the inventory problem reduces to finding an inventory policy that answers how much to order and when to order. So quantity and frequency both are the main questions here. If you increase the quantity, frequency will decrease, but increasing the quantity will increase the holding cost. Sure, it will reduce the setup cost, but it will really increase the holding cost. If you reduce the order and increase the frequency of order, then obviously setup cost will increase, holding cost will be decreased. So inventory modeling is just an art to balance between both, how much to order and how when to order. Okay. uh, the demand pattern in an inventory model may assume one of four types: deterministic and constant, static with time, deterministic and variable with time, probabilistic and stationary over time, probabilistic and non-stationary over time. We are dealing with a deterministic case now. Classic EOQ model, classic economic order quantity model. The simplest and inventory model, simplest of the inventory model involves constant rate demand with instantaneous order replenishment and no shortage. Okay. Uh, so we don't have a shortage cost here. Okay. We don't have lead time here. Let's define Y is equal to order quantity, number of units, D demand rate, T naught ordering cycle. Now, as the order quantity, for example, in our example, we have the order quantity of 100 kilograms. Okay, and demand per year, we have 1200. So we are going to order 100 divided by 1000, that is equal to, sorry, 100 divided by 1200, that is 1 by 12 years. So T naught is equal to 1 by 12 years. 1 by 12 year, that is 1 month actually. So that T naught is called as the ordering cycle. K, setup cost or order cost per order, rupees per order. Holding cost, holding cost is depend on inventory unit per unit time. Okay, so the total cost involves only setup cost and holding cost. Total cost per unit time, so we have to divide it by unit time. We obtain this K plus H Y by 2, as there is an average inventory average inventory involved during the cycle T naught is equal to y by 2. Therefore h multiplied by y by 2 multiplied by T naught. So finally we get d kd divided by y plus hy by 2. That is the TCU y. So we have to find the y. Take derivative with respect to y, equate to 0. We will get y star is equal to square root of twice kd upon h. So optimum inventory policy for classical EOQ model is order Y star in every T naught, Y star divided by D. So sorry, I forgot to add Y divided by D. So it should be Y star divided by T time units. Okay, I already mentioned that lead time and reorder. Okay, suppose we found out that in every uh, let's take that ice cream example. Suppose that I'm using that ice cream. Suppose it is imported ice cream, and if it is taking 1.5 month, if it is taking to 1.5 month after my order to reach here. Okay. Now, every time I'm ordering in 1 month, and I am getting in 1.5 month. Suppose for 1st June I ordered and I got the delivery on 15th July. On 1st July I will again order, I will get on 1st August. Likewise, that difference will be reduced and effective lead time will be reduced. For example, for uh, for 1st July I got order of 15 July, which I ordered on 1st June. So effective lead time is just only 15 days. Okay. Okay, let's take an example of a neon lights on a campus that are placed 100 rate of 100 per day. Okay, so we have D is equal to 100 per day. The electric plant orders the neon light periodically. It cost rupees 100 to initiate the purchase order. So K is equal to 100 per order. Neon lights kept in a storage estimated cost O per unit. For per unit, so holding cost is equal to 0.02 rupees per day per unit. Okay, lead time between the placing and receiving order, that's 12 days. Very good. So L is equal to 12 days. So by using all these quantities, we will calculate Y star. We got Y star is equal to 1000 lights. Now let's calculate the cycle. Cycle is equal to T naught is equal to Y star upon D. Y star is equal to 1000 divided by 100 is equal to 10 days. So on every 10 days, the department has to order how much? 1000 lights. Okay, but there is a problem. Because there is a lead time L is equal to 12 days and order cycle is 10 days, then we have to divide it. L divided by T naught, that's 1.2 or something. Take integer part 1. So L minus N, that is 1, multiplied by T naught 10. It gives us effective lead time is equal to 2 days. Okay. So during that lead time of 2 days, and per day we need 200. So order, sorry, for lead time of 2 days and per day we need 100 units. So reorder point is equal to 2 multiplied by 100, that is 200 units. So inventory policy is equal to order 1000 units wherever the inventory level drops to 200 units, and the cost can be calculated by kd upon y plus hy divided by 2, that's 20 rupees per day. Okay. Now, many times what happens whenever we order higher quantities, higher number of quantities. For example, if we ordered 100 units, there is a different price for per unit, and we order 115 units. For that, price is different. It is called as price breaks. Okay, in which we create the difference. For example, Q is the price break. Consider Q is the price break, and if we ordered Y less than or equal to Q, then the for price purchasing price for per unit is C1, and if you order greater than Q, then the price is C2. Okay, purchasing cost per unit time can be calculated by d multiplied by c1 with per unit time, so d multiplied by c2. Total cost per unit time can be calculated by putting this purchasing cost in setup cost and holding cost. Keeping that purchasing cost in mind, we can calculate total cost per unit by TCU1 and TCU2 just by changing DC1 and DC2 in that previous, that is the setup cost, purchasing cost and holding cost. These two quantities are different only. Okay. For the determination of economic order quantity, we need to calculate, firstly we have to calculate ym. What is ym? Ym is equal to square root of twice kd upon h. We have already seen that. Now by using that ym, we have to uh, create three zones here. Zone 1, 0 to ym, we already have defined ym. Ym to q, we have to find out this q, and q to infinity. Let's go to figure 4. It will show us this 0 to ym, square root of twice kd upon h, ym to q, and q to infinity. Now we have to find zone 1, zone 2 and zone 3. How to find this zone? How to find this q? So the q can be find out by tcu to q is equal to tcu1 of ym. Now tcu, I forgot to put 1 here. Tcu1, tcu of 1 can be obtained by putting y ym here, and we will get tcu1 ym. Okay, for the quantity q, as we don't know whether q is greater than ym or less than ym or whatever, we don't know, so we will put here c2d kt upon, we will replace y by q only. Okay, then by solving that equation we will get such quadratic quantity. Okay, uh, and let's move for the following steps, following algorithm for obtaining the EOQ for the price break. Determine Y, which we have already did. Now, if Q is in zone 1 is 0 to YM, then Y star is equal to YM, no need to go to step 2. But if small q, that is the price break, is not in a zone 1, that is it is greater than ym, then we have to calculate q by that quadratic equation. By that quadratic equation, solve that quadratic equation, you will get capital Q. Okay, uh, define zone 2, zone 3. If small q is in zone 2, that is ym to q, in between ym and q, then y star is equal to q. Otherwise q is in zone 3, then y star is equal to y, which means for zone 1 and zone 3 it is ym, and in between ym to q it is q. That is the price break EOQ for the price break. These are the graphs which we have already discussed. Let's take an example of a garage. The garage buys car oil in a bulk at $3 per gallon, discounted to 2.50. Okay, so C1 is equal to 3, C2 is equal to 2.5. Order quantity is more than, okay, $1,000. So okay, small q is equal to 1,000 gallons. The garage services approximately 150 cars. Okay, each oil change takes 1.25. Okay, 150 multiplied by 125 gallons, this is the demand, 187.5 gallons per day. Okay, d is equal to 187. Company stores bulk oil at cost of, okay, 0.02, that is the h holding cost. Cost of placing order k, $20. Lead time 2. Okay, using these quantities we can calculate ym is equal to 612.37. Okay, so we got ym here. Okay, and it's less than 1,000 as per our ym is equal to 612, and it is less than 1,000. Okay, Therefore, ym, okay, case 2 or case 3, just we have to find out whether the capital Q or it is greater than capital Q or it is less than capital Q. Okay, let's find out this. First we need to calculate, TCU1 of ym. We will calculate this. We got that by DC1 formula 574. Now putting this 574 in the quadratic form, we will get Q is equal to 10,564. Now we are in a case 2. Here 600 something, 1000 something, sorry, 1000 something, 1000, and it is 10,000 something. So now Q is in zone 2. For the zone 2, we have y star is equal to Q. If Q is in zone 2, y star is equal to Q. So our EOQ is equal to 1000. Q is equal to 1000. Okay. And for 2 days, for one day we have 187.5. So the reorder point is 375 gallons, and the optimal inventory policy is order 1000 gallons when the inventory level drops 375 gallons. Now moving to the random demand probabilistic EOQ model. Here demand is random, but particularly demand in between the lead time is assumed as a random variable. Okay, the model is based on three assumptions. Unfilled demand during the lead time is backlogged. From this figure you can observe that we have inventory level 0 here, we got inventory level up to y, we got order, and that curve you can observe it is random, not like deterministic EOQ model. Okay, and after 0, even after 0 it is decreasing, though it is showing negative inventory. It may be from that reserved stock we have used, a buffer stock. Okay, that is the demand during the backlog demand only. Okay, so no more than one outstanding, so lead time should not be greater than T naught, that cycle. Okay, the distribution of the demand during the lead time remains stationary with respect to time. Okay, so it should not be the function of time. Okay, from this we can observe that R is the reorder point. When the inventory level reaches to R, that shopkeepers orders Y amount, and it reaches, and that what happens due to the random demand at certain time point before getting that that order reaches to 0, that inventory level reaches to 0. Okay, this is happening just because it is probabilistic. Okay, many times this will also be possible that demand is less, here demand is more compared to the reserve. Okay, let's assume f of x is the PDF of the demand during the lead time. Dk are with same notations and same logic. Just add P. P is the shortest cost per inventory, also known as a penalty. Many times we use P for the probability, but here it is not for probability, it's for the penalty. Setup cost KD upon Y, it's same as KD upon Y. Expected holding cost, for the previous case it's just only Y divided by 2, because starting it is Y and ending it's 0. Y plus 0 divided by 2, therefore Y by 2. But here there is a small change. We have to add this quantity R minus expected X. What is expected X? Expected X is the demand during the lead time. Okay, if it is greater than, if X, that random demand is greater than X, then that term, this quantity goes in negative, and if it is less than R, then it is positive quantity. Okay, so the on an average expected holding cost can be calculated by H multiplied by H, where I is equal to Y by 2, which is fixed as like a deterministic, plus R minus expected X. Okay, expected shortest cost. expected shortage cost can be calculated by using S, where S is the expected value per cycle. Okay, shortage occurs only when X is greater than R. That time demand is greater than the reserve one. Therefore, X, which is the demand, minus R, which is the reserve, okay, R to infinity, that demand is greater than R to infinity, that shortage of X minus R multiplied by f of x dx. Okay, this is the expected shortage multiplied by penalty. Okay, so total cost can be calculated. This is the setup cost dk upon y. This is the I quantity h multiplied by r. This is the holding cost. Penalty multiplied by that s expected quantity we have already, expected shortage quantity we have already calculated. Now we have to calculate y, we have to calculate r by using the equation 2, take derivative with respect to y with respect to r. Solve this equation, we will get two equation 3 and 4. But observe that equation, y star is equal to square root of 2 kd plus p into s. What is s? S is this quantity and it completely depends on r. Okay, and look at this quantity, r star to infinity f of x dx. This is 1 minus cdf of that distribution, but 1 minus f of r, so it depends on r. We can calculate r and y star by using these two equations, but as above equation is quadratic and below equation is integration type, so it is quite complicated. So Hadley and Benton came up with an idea algorithm to solve this by using iterative procedure. What they have done, for r is equal to 1, they converted 3 and 4 equations to y hat and y curl. These are the formula. And unique optimal value of y only exists, y and r both exist when and only when y curl is greater than or equal to y hat. So firstly we have to verify this condition, we have to find out y hat and y curl, and if uh, y curl is greater than or equal to y hat, then we have to follow the following steps. Firstly, let r0 is equal to 0, find y1. What is y1? Y1 is equal to y star is equal to square root of twice kd upon h. Set I is equal to 1 and go to next step. Now determine Ri by using that y value. We have put that yi here, obtain h into that quantity. We already, suppose we know the distribution of that demand, 1 minus f, by using one inverse CDF, find out the value of r. Put that r value in next y. Put that y value in here, obtain s, put that s here and obtain y. Keep this processing iterations go and go unless and until there is y and yi plus 1 are approximately similar. Okay, this is the iterative procedure. Let's take this with an example. Suppose Electro uses resin in its manufacturing process at the rate of 100 gallons per month. Okay, so we have a demand of 100 gallons d. It costs, okay, $100 to place an order, k is equal to $100. The holding cost per h 2, shortage cost per dollar 10, p is equal to 10. Historical data shows demand, okay, uniform x follows uniform 0 to 100, so we have a for x and expected x. So we know all these quantities. Now firstly we have to calculate y curl and y hat, so that checking the existence of unique optimal value. So y hat is equal to 774, y curl is equal to 5000. Okay, the condition is y curl greater than or equal to y hat. Okay, we have 5000 greater than or equal to 774, so we have unique optimum value. So okay, here we need s. We know that f of x, we can obtain an expression of s in the form of r, or expression of r in the form of s. Okay, so s is equal to r square divided by 200 minus r plus 50. Okay, by using reverse engineering we can obtain r expression for r also. Okay, so yi is equal to, this is the equation fifth, that integration, that value ri is equal to 100 minus yi. So now instead of that 2 3 and 4, 3 and 4 equations, now for particularly for this example we have 5 and 6. Now put that values, obtain iterations for y1 y2 and y3, r1 r2 and r3. So we have 316.23, 319.37, 31.44. Now both are approximately same. Here also our quantities are also approximately same. So we can stop here. Approximate quantities are sufficient for us. Let's move for the single period model. Okay. This section deals with the inventory item that are in stock during the single time period. At the end of the period, best example for the single period model is a newspaper model or a newspaper vendor model. Uh, we all know that that newspaper vendor only sells his newspaper during the morning session 6 to 9, and after 9, or suppose after 5 or 6, no one is going to buy that newspaper. Okay, so for that single period model is the concept. Okay, everything every notations are same. uh, ec- Consider one submodel related with the single period model. No setup model. Okay, no setup cost. Okay, news vendor model. Consider that news vendor model. Demand occur instantaneously at the start of the period, immediately after order is received. Okay, suppose order received, y amount, no setup cost. Okay, demand, so demand is less, so that newspaper vendor has to keep all that y minus d newspaper to himself, and after one day he has to put it in a scrap or resale or do something whatever. Okay, or in the other case, suppose y inventory is less than the demand, that d minus y be the shortest, and for that shortest he has to pay that penalty. That is the case. That is the model for the single period model. Okay, okay, here there is no setup cost. Observe this. Okay, uh, okay, we will move. So the expected cost for the period. Now for this period, he has to hold everything, every y minus d units here for the whole day, and he has to pay something for that. That is the holding cost. And if he could not uh, sell, he could not sell due to the shortage, then he has to pay some penalty. Then uh, we can obtain the probabilities by using y minus d f of the, same as whatever we had done for that s, but 0 to y, as the demand is less than y, and here demand is greater than y. So when demand is less than y, we have to pay the holding cost. When demand is greater than y, we have to pay the penalty tax, the penalty. Okay, so we have to minimize this uh, quantity, this expected cost. Okay, by solving these expressions, we can obtain P probability of t less than or equal to y star. That is the CDF of CDF f y star is equal to P upon PS. Don't forget P is upon penalty, not probability. P upon P plus H. Okay, we know that demand may be continuous or may be discrete. It may be possible that demand may be discrete or continuous. For that case, the algebraic manipulation can be done for that. CDF P upon P plus H must lie in between y and y minus 1. CDF of y star and y star minus 1. So we have to find that y star. Okay, consider the example where, okay, the owner of newsstand wants to determine the number of newspaper now to be stocked at the start of the day, that he has to calculate the y. The owner pays 30 cents for a copy. Okay, that is the purchasing cost, and sells 75 cents. Very good. So 75 minus 30, that is the cost, 45 cents. He earns 45 cents by each copy. The sale of newspaper typically occurs between 7 to 8 a.m. Okay, newspaper left at the end of the day are recycled for an income of 5 cents. Okay, there is a loss. He has to pay 30 cents and he will get only 5 cents. Okay, very good. Okay, let's go for that example. Now, suppose if the demand is less, he buy he bought that newspaper for 30 cents, and after a day he will get only 5 cents. So there is a loss of 25 cents. So at this time point, holding cost of a paper for a day is 25 cent. Okay, and here, if demand is more, his demand is more and he has less quantity, then suppose for each copy he is getting 45 cents. So there is a loss of 45 cents for that d minus y quantities. Okay, so this is the penalty of 45 cents. Okay, each unsold copy will cost the owner 30 minus 5, 25 cents, that is equal to h, that is the holding cost, and the penalty of rupees 45 cents per copy per day, that is p upon ph is equal to 0.643. By inverse CDF we will get, as the d is normal distribution with 3000 mean and standard deviation 20, we can obtain by using inverse CDF y star is equal to 308 copies. And as it is given discrete, we just have to calculate the cumulative probabilities. zero point 0.1, zero point 0.3, 0.7. 0.7 is greater than 0.643, and zero point 0.3, zero point 0.3 and zero point 0.7. So it must be y star is equal to 300 copies. Now another policy or another model is called as a small s and capital S policy, SS policy. Okay, uh, there is no big difference between 7.2 model and 7.3 model. There is just addition of setup cost only. Okay, now we all know that the setup cost is fixed, it is not changing with respect to the order quantity. Therefore uh, we can use that expected C bar y. It is the notation for setup model, SS policy model. Okay, expected cost for setup model is equal to addition of setup cost k plus expected cy, and this quantity is expected cy. As k is constant, minimum of c expected c bar y must also be same as that y star. But for y star we already calculated that probability of y less than or equal to y star is equal to p upon p plus h. We have to use the same formula. So by using this equation, you can observe that expected value of c bar y is equal to k plus expected value of c of y. So by solving this equation, expected value of c of s is equal to k plus expected value of c of s. Okay, we have to put here capital S is equal to y star. Okay, so we have to find such a small s, for which expected cost is equivalent to the y star for that previous model, k plus expected value of capital S. Here capital S is equal to definitely y star. Okay, okay. Now what happens whenever we use this model? This model gets converted in the quadratic form, and quadratic forms the small s quantity gives two values. Okay, and if one of the value is greater than capital S, then you can discard that value. Okay, So here smallest quantity is important for us. We will calculate the smallest quantity by using this equation. Assume that x is the amount on the hand. Okay, we have x is the amount already in a hand. Okay, so how much should we order? The question is answered under three conditions. Okay, suppose we already have calculated small s. Oh, x is less than or equal to small s. So we need to find x less than or equal to small s. So we have to order in that condition. In that condition, x less than s, we have to order capital S minus x. If the order is in between, I think we should go for this. Okay. If the order is in between s and capital S, there is no need to order. From this we can observe that if and only if x is in between 0 to s, we have to order s minus x, and in above case s to capital S and capital S to an above case, we don't need to order any quantity. Okay, okay. In both 2 and 3 cases, not advantageous to order y star is equal to x. Okay, let's move. Let's take an example. The daily demand for an item during the single period occur instantaneously at the start of the period. The PDF of the demand is uniform. Okay, X is uniform again. So it's 0 to 10. The expected holding cost of the item during the period is $0.50. The unit penalty cost P 4.50, H zero point 0.5, a fixed cost of okay, K is equal to 25. Determine optimal inventory policy for the item. Okay, to determine y star, we have to calculate P upon P plus H. P upon P plus H is equal to 0.9. As demand is uniform 0 to 10, for zero point 0.9, we have S is equal to y star is equal to 9. So we have to calculate expected value of C of y is equal to, okay, expected value of C of y. What is expected y? Expected value of C of s. We have to calculate expected value of C of that s is equal to y star. We have already calculated y star as a 9. So we have to calculate expected value of C of 9. Add k and solve this equation. So expected value of C of y, we got this quadratic equation here. So expected value of C of s, we have to find small s is equal to k plus expected value of C of s. Okay, expected value of C of s is equal to, put that s in same equation, add k here, add k here, solve this equation, we will get s square is equal to, s square is equal to, putting 9 here. Okay, s square is equal to minus 18 minus 19. Okay, we can tell that we have minus 9, s is equal to minus 1, or s is equal to 19. Now we have already decided that if small s is greater than s, it is discarded. So 19, this value must be discarded. Okay, because the remaining value is negative. Okay, that is the infeasible range. S has no feasible value. Okay, as figure 9 shows, this figure 9 shows the optimal inventory policy in that case calls not ordering. Okay, thank you.